Welcome to CERIAS 590E, the security seminar for the week of September 6th. Today our guest speaker is Dr. Jens Palsberg. Dr. Palsberg got his PhD from the University of Aarhus in Denmark. After that, he spent some time as a visiting scholar, or visiting scientist, at various institutions, including MIT. He joined the faculty here at Purdue University in 1996, and since then has authored well over 50 technical papers, at least one book, and has several accolades, including the National Science Foundation Faculty Early Career Development Award. If I've left anything out, I hope you'll be sure to fill in, and otherwise I'll turn it over to you.
Thank you, and thank you for coming. Today I want to tell you about a project that has been going on in our research group the last half year, since March. This is joint work with Dennis Breiler, who's actually here, and Niels Damgaard. And to all the people in the closer part of the galaxy, I want to say a big hello to all the live phones out there. This is a project about interrupt-driven software. And what we're interested in is to make it easier to write software that works. The application domain for this is something like Palm Pilots, where every time when you sit with your Palm Pilot and you touch the screen, if you haven't done something for a while, then the machine is actually totally dead. What happens is that you touch the screen, an interrupt arrives, and it's caught by the operating system, and the operating system figures out what to do. And of course, one of the things you're interested in is that the latency between the interrupt happens and something then takes over, an application takes over and does what you want, should be as short as possible. There are also various kind of programming errors with interrupts and stuff that one wants to avoid, and I will tell you more. Another application is cell phones, where again, some of the cell phones that are around today are basically interrupt-driven things. When events happen with the phone, interrupts happen, and the software then does what it's supposed to. The angle we came from in the project is from microcontrollers. So a microcontroller is a sort of one of these little embedded systems that typically sits in a barn, for example, and will get signals in about temperature, and then if the temperature goes too high, it will start the fan or something to get the temperature down and continuously monitor various things. When you look at these applications here, both in the Palm Pilot and in many of the cell phones, we looked at the processors is one of the Motorola 68000 kind of processors, one of those family processors. For example, in the Palm Pilot, there's a Dragon Ball processor, which is a Motorola 68328, something like that. And there are sort of variations of this. One of the things that makes life interesting here is it's not just one interrupt we're talking about. There's a whole bunch of them. On the Dragon Ball processor, there's typically sort of, if it's the standard one, 18 different interrupts that can happen. And if we are looking at the processor we're actually working with here in this project, which is a Z86, it has 6 interrupts. And as you will see when we go along, it actually matters how many there are, because the more interrupts there are, the more space and time will it take up to analyze the software. The business we are in is for software like this, which is heavily driven by interrupts, write tools that help looking at code like this. So imagine you've written an application. This is actually Z86 assembly. We wrote this program here for the occasion. This program is not doing anything terribly interesting, but it is a running Z86 assembly language program, and if you sort of look at it a little bit, you will see that there's some stuff in the beginning that defines that you see that it says in line something like it says interrupt vectors. It starts saying .word handler. So this is where it says, look, the interrupt handler for a particular kind of interrupt we will find at the label handler, which will then be later in the program. And then the main program begins, and if you look at the rest, which is on this page, you will see the handler is down at the bottom. And then after some initialization code, which was on the previous page, there's a start of the main loop. You can see it says start, and a few lines later jump start, so there's a main loop there. And the main loop calls a procedure send, and also the handler calls a procedure send, and then things happen. You can see at the end of the handler there's an IRET, which means return from interrupt. So one of the things that can happen here is an interrupt arrives. It can arrive at any point. And either interrupts are turned on or they're turned off. And if it's turned, well, in some sense, in both cases, the interrupt will go into a particular register. And then whenever the interrupt is then turned on, now the processor will say, okay, there's an interrupt that has arrived. And then control will jump to the interrupt handler. And then the interrupt handler does its business, and if it likes, it can then say interrupt return, I read, and control will go back to where it was. An interrupt on this processor and also on the Dragon Ball processor, interrupts can interrupt each other. So you go to the handler and a new interrupt can arrive in the handler, and if interrupts are turned on, you can interrupt the interrupt. They can arrive at any time, they can interrupt at any point, no matter what else you are in the business of doing, unless of course the interrupts are turned off. So this gives a much more complicated control flow than what you usually see if you are looking at a C program or some other Java program or something. So what we're interested in is writing tools that can help with programming this and get it right. So what we're looking at is a tool we built here. It doesn't have a name, we've got to figure out a name at some point. So what the tool does is that it helps with three things. So it has a capability for analyzing stack size, and this is important on the Z86. So you see, we're working with the Z86 because this tool was our first prototype, and we wanted to be sure that it could handle what we are throwing at it. So the Z86 has its stack living in registers. There is no RAM. So there are 256 registers. There's 4 kilobytes of ROM for the program. So the program is in the ROM, and the stack and whatever other data you want to keep around will be in those 256 registers. If we were going to scale this up to the Dragon Ball processor, or some other Motorola 68000, this would mean moving up to 18 interrupts on the typical Dragon Ball and much larger programs. So we're talking about 8 megabytes of storage on those. And it's not at the moment clear that our techniques would scale up, but we're working on it. So what we're doing here is that we're looking at a situation where the stack lives in the registers, and the last thing you want is that the stack can keep growing, because you have to set aside a certain amount of stack space, and then they're using the other registers for other things, right? All programs need registers. If they want to be reasonably fast, you cannot leave everything on the stack. So the stack is in part of those registers, but not all of them. Of course, even if the stack was in all of the registers, there's still a bound. It cannot be bigger than 256. So the first thing here is to get an ironclad guarantee that the stack will never grow bigger than whatever amount of space we have set aside for it. And this is not trivial, because you see, when an interrupt arrives, the address where you are now will be put on the stack, because you want to be able to say I return and come back. Right? So the address has to be somewhere. It's put on the stack automatically when the interrupt comes in. And actually more than that, a bit more information, some status registers are also put on the stack. So this means that an interrupt arrives, something goes on the stack automatically. If you're now in a situation where this interrupt handler that is now running after the interrupt has happened, if that thing again gets interrupted, then of course the information, the return address is on the stack. If it gets interrupted again, more stuff gets on the stack, right? And if you sort of keep going, if there's some unfortunate loop, then this is the recipe for having a stack that grows without bounds. And it's not easy to see when you just look at the code whether this is one of those where the stack can grow in an unbounded way. And the reason is that interrupts can be turned on and off during the computation. So there are instructions that will turn on and off interrupts as you go along. And so you can imagine that if you want to know if an interrupt is turned on, you need to really follow the control flow path up to the point where you want to know it. And at the same time, of course, the control flow is complicated because there can be interrupts, right? So if you want to know the control flow, you need to know the interrupts. If you want to know the interrupts, you need to know the control flow. So this is not simple. A second thing we want to know is things are put on the stack for various reasons. One of them is because of the interrupts, so that's one thing. Another one is normal procedure calls, where you put the return address and nothing else. The third thing is that on occasion it's nifty to put other things on the stack. And the key now is that there will then be times when we take things off the stack again. We want to be sure that we don't get conflicts, so that you push a return address and then you try to pop something else. On this processor here, in some sense, it's not disastrous that suddenly the program wanders off. It's not disastrous in the sense that you're not going to get a bus error, or you're not going to get a core dump or anything like that. The processor will happily continue executing no matter what. However, it will probably not do what you wanted, right? So one of the ways of checking that at least something sensible is going on in the program is that every time you do a pop, where you explicitly pop something, or you do an I return, where you return from an interrupt, or you do a return, where you're just returning from a normal procedure call, that at least the kind of thing on the stack is the thing you are expecting. So if you're doing a return, there will be a return address. If you're popping something of type integer, for example, there will be an integer, or whatever it may be. So that's the second thing the tool does. The third thing it does is what we are actually really excited about, is interrupt latencies. So if you look in the one of these Motorola manuals for the processors running on the running in the Palm Pilot, you will see tables with latency. So it will say, well, if you are now clicking or touching the screen, the latency before something happens will be at most blah, right? And one can wonder where they got this from. I think they got it from testing it a lot and taking some averages, and that's the expected latency. What we are after here are upper bounds. We want to have, just like we want a sure upper bound on the stack size, so it will never happen the stack grows bigger. We want to have a sure upper bound on the latencies, so that no matter what happens, no matter when, on which program point the interrupt will arrive, it will not take more than this many microseconds or milliseconds before the interrupt gets handled, right? So that's the kind of stuff we're after. So we have a tool that does this. It's implemented in Java, and what I'm going to do here is I'm going to tell you a bit about what the tool does in a bit more detail and how it works. And I'll show you some numbers in the end. So we have access to 7 commercial microcontrollers from a company up in Milwaukee that we cannot show you the programs. They're proprietary, but they gave us permission to work with them for the purpose of analyzing them. And what I can do is I can show you the numbers we got out when we analyzed them, but I cannot show you the programs themselves. You see, what we're going to do now is that we will build a control flow graph. So this is sort of a standard compiler maneuver where, to be able to do anything when you want to compile, compilers build control flow graphs. And we're going to do the same thing here. We don't want to compile anything, we just want to analyze the program. So we'll take the text of the assembly program, and we're going to build a graph that shows how control goes from program point to program point. And now there's a design decision, which is sort of the major thing we were struggling with in the beginning, which is, okay, at every step of computation, of course, we can look at the Z86 machine state, which consists of all the values in the 256 registers, and each register is 8 bits. Then we could say, okay, that is the machine state, and then we can make a giant graph with one node in the graph for every machine state. So this would be, the worst case of this would be, well, 2 to the 256 times 8 bits for every register. And that would be one node for every possible machine state. And then we can start drawing edges in the graph, saying if you are in this node right now, the next instruction is this, it will do something to the machine state, and so we will go over here. Right? That would be a completely precise description of what goes on in the program. However, that's a lot of nodes, so we don't have space for that. We don't have time to build the graph. It just takes too much time and space. So what we're doing instead is we're saying we can only model some of this machine. So we have to make some choices, and we're not going to model all 256 registers, so instead we're going to model some of it. And the question is how much. And when you look at what compilers do, what they typically do is that they model just one register. They model the program counter. So that can already be a whole lot. So I'm sort of in the program analysis community, among other things. And when you look at the size of programs people usually write there, and are able to run through analyzers that do serious analysis, more than just sort of normal vanilla compilation, the limit has recently been pushed to about 2 million lines of C. So in the beginning of the 90s, people were quite happy if they could get a serious sort of really hard-hitting analysis to work for 30,000 lines. About 4 or 5 years ago, the limit was pushed to about 300,000 lines. And now people are publishing papers where the limit is up to about 2 million lines. So for example, for C, point-to analysis, which is the idea of finding out if two pointers in a C program point to the same memory or not, can now be executed, for example, for Microsoft Word, which is in the current invocation is about 1.5 million lines of C. There's an analysis up in the Microsoft Research Lab in Redmond, which can do this in about 20 minutes. And there's a tool out at Berkeley that can do the same kind of analysis with some twists for C programs, and they can do about 2 million lines of C in about 35-40 minutes. So you can see just modeling what these analyses do is they model just the program counter and very little extra. But already that is a fair bit of you can get, if you have 2 million nodes in your flow graph for each line in the program, that's already a fair bit. So here we are talking about much smaller programs. We're talking about programs that fits in 4 kilobytes of ROM, and since some instructions are more than 1 byte, we're in practice talking about 1,000, 2,000 lines of code, no more than that. So modeling the program counter here is not a big deal. However, it's necessary to model more than the program counter, and this is what I will argue for now. So there's this thing on the machine that controls whether interrupts are turned on and off, which is the interrupt mask register. And what it has is 7 bits. So there's 6 interrupts, and 6 interrupts, and they're actually prioritized. So there's one interrupt that has more priority than the other one, so that if 2 interrupts arrive at the same time, then the one with the highest priority is going to be the one for which control it's the one that gets handled. Other than that, there's a 7th bit, which is like what I call the master bit. So the master bit, if it's on, in some sense, then the other 6 bits rule. If it's off, then all the interrupts are off, right? So if it's off, everything is off. If it's on, then you have to look at the other 6 bits to see what is on. And now, for a moment, imagine that we don't model this mask register. So when we build the control flow graph, imagine that there will be no information about this register in the graph. So now, let's say that an interrupt arrives at a certain point. So that's great. So control goes to the beginning of the handler. So interrupt is turned on, say. So that's exactly the problem. Is interrupt turned on and off? If we in the graph only know where we are, so it's like if we keep a finger in the program text, we are here, and in the graph this is modeled by a certain node. Then what does it mean when an interrupt arrives? Of course, if we're looking in the processor, we can look in the mask register and say our interrupt turned on and off. But if we are not modeling that in the graph, if we are in a certain node and it doesn't say what value of the mask register is, we don't know if it's turned on and off. So we have to assume something. And the safe bet is to say, well, they're probably turned on. So if they're turned on, okay, so control goes to the interrupt handler. And what happens in the processor, when you run it on the processor, is that when you go to the handler, the master bit is turned off. So it happens automatically. You take the step, you get to the handler, the master bit is turned off. Now you can sort of safely start doing operations. You're not going to be interrupted there. But of course, if you like, and this is what happened many times, is that at some point you need to turn this thing on again so interrupts are turned on. And as soon as you turn it on, another interrupt may arrive, and if you turn it on before you leave the handler, which is what you ought to do, then of course you can get interrupted. Right, and since the graph I'm talking about does not have no information about whether the interrupts are turned on and off, well, it looks like it's turned on all the time. So you start the handler, you can get interrupted immediately. You jump back, you get interrupted immediately, and you get the stack that grows without bounds. And the first thing we want to check is that the stack cannot grow without bounds. So the morale of all this is, if we just model the program counter, it looks like interrupts are turned on all the time, and therefore it looks like the stack can grow unboundedly, and we have a useless tool. So we need to do something more. So the next thing you can think about is, let's just model the master bit, because what happens when you jump to the handler, the master bit is turned on, so all we need is just to model the master bit. So now you imagine that in a node in the flow graph, there will be the value of the program counter, so it'll be a pointer to where are we now in the program, and then there'll be 1 bit, just 0 or 1, saying at this point interrupt are turned on or they're turned off. So that would be an improvement. But in some sense now there's 2 copies of every piece of every line in the program. There are 2 nodes in the program for each line. So we just doubled the size of the graph. So this is not so good either, because this doesn't take into account that when you get to the handler, you turn on this master bit at some point, then great. So now we can model that. So at least we have in the graph that we're not going to get interrupted there. But you turn it on at some point, and at that point again, if you don't know what the other bits are, we have to assume that they're turned on. So now all the interrupts are turned on again, and one can sit down and construct examples where very quickly you get a graph that, from the analysis point of view, grows in an unbounded way. So what we're going to do is model in the graph both the program counter and the whole IMR register. And think for a moment what this means. The programs are, let's say, 2,000 lines. So that takes 11 bits to model the program counter. And the IMR is 7 bits. So now we're talking about 2 to the 18 nodes in the worst case, right? Well, and we have space for that, so that's fine. So now one could wonder, should we model more, right? The worst case is still model all of the registers 2 to the 2048 nodes. And here we're just talking about modeling 2 to the 18 nodes, which is much smaller. But there's sort of middle ground. What we're trying to say here is we're getting nowhere if we model less than those 18 bits. So let's model those bits, and here's the graph. So this is actually the graph for the program that I showed you. And what you see is that how many nodes are there? So there's 20, 25 nodes, something like that. It's actually not very much. It's actually not very much more than the number of lines that was in the program. So it's not like we get a worst case situation where in some sense, every possible value of the IMR is paired up with every possible value of the program counter. We get something which is much easier. The way this notation works is that in every node you see 2 numbers. So to the left of the bar in the node is the program counter. We're counting in hex here. And to the right of the bar you will see the first bit is the master bit. And here we're actually only working with one interrupt. There's only one handler, right? And the second bit is then the bit for that interrupt. So for this interrupt to be turned on, both of these bits have to be 1. If just one of them is 0, interrupts are turned off, right? So now we can follow this graph and we can see what happens in the program. So control starts up in the upper leftmost corner, and in the beginning, okay, the program counter is at the very top line of the program, and the whole IMR is 0. So I'm just showing you 2 of the bits. The other ones are not used here. And then some initialization happens, and the interrupts are turned off all the way. And then when we get to the label start, which is this node in the upper rightmost corner, this is the point where we turn on the interrupts and we enter the main loop. And and you can actually see the main loop is going on out there in the pretty much if you think of the rightmost column, that's sort of pretty much the main loop. So something is going on there, and we're moving from node to node and cycling back and all that. Now the interrupt handler is the node in the leftmost column, second from the top. It says handler, right? So from lots of nodes where the interrupts are turned on, there'll be an edge that goes to the interrupt handler. And what's going on there is, well, if an interrupt is turned on, if an interrupt arrives at a certain node, then control can go there. And now you will see that on the edge, there's this common edge that goes over to the handler node. There's this bang free. And what it means is that it's a way of remembering that when an interrupt fires and control is transferred to the handler, 3 bytes are put on the stack. So 2 bytes for the return address and 1 byte for the status register. And since we're interested in stack size, it's important to know when things go on the stack and when it doesn't. And then when control goes to the handler, well, so you can sort of wander around, and then sooner or later you can do an interrupt return, and you can sort of wander back to the main loop and continue doing things there. So one of the things you can see in the program is that from all of the nodes where you can go to the handler, both of the bits are 1. And when control goes to the handler, immediately the master bit is turned to 0, right? So that's the way the processor works. So you'll also see that there are edges in the graph that have a question mark on them. So all the things with a bang, that means things are put on the stack, and the number tells how many bytes are put on the stack. When there's a question mark, it means that things are taken off the stack. And again, the idea is the number after the question mark says this is the amount of stuff that's taken off. So one of the important things now is, can the stack grow infinitely? So one of the whole points now is that since we are modeling both the program counter and the IMR, we have this great hope that at least we're not running into one of the traps from before. So there's hope that this graph can tell us that the stack doesn't grow infinitely. So let's see how big the stack can get. The worst thing that could happen is that there's a loop in the graph where you keep putting things on the stack as you go around the loop. This would mean that the analysis believes that the stack could grow unboundedly. You just enter that loop and keep going. Now, if you look at the graph, first you wander along in the top there, and there are no bangs, so life is going great. Then move down to the node in the rightmost column, 2011. So that's the point where we can now take an immediate left there. 2 bytes is put on the stack, and take another left, and 1 more byte is on the stack. So that's now 3 bytes on the stack. Then we keep going with now we could keep going with some innocent edges, but instead at this point we'll take an interrupt. So from the node 2811, we're going to take an interrupt that will go to the handler. So that will put 3 bytes on right there. So now we're up to 6 bytes. And when we're in the handler, we take a step down to 3501. And now what we can do is that we can start going right. So take a step to the right and another step to the right, and you'll see that first 2 bytes and then another byte is put on the stack. So now we're up to 9 bytes. And as it happens, if you look at what you can do once you are at 2801, there's not much you can do until you get down to 3001, unless you want to enter this loop that does nothing to the stack. You go down to 3001 down at the bottom, and from now on, the only thing you can do there is that you can start taking things off the stack again. And now the key is that this graph is constructed in such a way that you don't need to worry about the edges. When you look at the stack size, you don't need to worry about taking things off the stack. It's enough to look at the edges that either do nothing to the stack, so they have no label, or else they have this E as a label. E means innocent in this case, means no change to the stack, or else they put things on the stack. So all we need is to look for the worst case in the way I did it. So what we're getting here is that for our program, the maximal stack size is 9. So you can try to find a way of getting more things on the stack, and there is no other way. I gave you the worst case. So the worst stack size is 9. So this means that we can now, if we want to program put this program on the processor, we can now just set 9 bytes aside for the stack, and we can use all the other registers for other purposes. So there are other things we can use the stack for. So one of them is to we can use this graph for. So one of them is latency analysis. So now the question is, an interrupt can arrive at any point, whether the interrupts are turned on or off. So if they're turned off, well, they will wait in this register called the IRQ register. So the interrupt will just set a bit in that register, and then the processor will keep looking at that register, and at the time when the interrupt is turned on, then you'll say, great, the interrupt is here, and it will go to the handler. So now the question is, how are we going to find out what is the longest latency? So, of course, up at the initialization phase in the top row, interrupts are turned off all the way. So, suppose an interrupt arrives right at the beginning at the node called init here. So now the interrupt is just waiting, and we're going through all of the 6 nodes until we get to the start node. At that point, the interrupts are turned on, so we can take an interrupt right there. So what does this mean? Well, it means that sort of 7 steps of computation is the longest latency we get if an interrupt arrives in the initialization phase. Other than that, the longest latency we can get happens if we're looking at the node, which is called, let's see, it's in the central column there. So let's see. So take a node in the middle. For example, the node just above the bottom in the middle, 2E01. So imagine an interrupt arrives there. So how long latency are we going to get? So you can take one step down to 3001, and then you take another step to, for example, 3211, and then you can, from that point, interrupts to turn on again, and you take an interrupt. So that's sort of 3 computation steps, and one can look around and one can find some other ones. I think you can actually improve a little bit, but the point is that it's kind of a graph search to find out whether where the longest path is. Back to the handler. However, in this particular graph, there's a problem. Imagine that you get an interrupt that arrives at node 2801. So it's it's sort of right in the middle there. One of the guys with a big black it's more round than the other ones. Has a thicker edge. So if an interrupt arrives at that point, if you look at the graph, interrupts are turned off at that point because the master bit is 0. And what can happen now is that the control can go around in a loop. So you see there's a loop there, 2801, not 2901, 2C01. And from the graph point of view, control can just keep going there. If one looks closer at the program text, this is not the case. You will always break out of this loop at some point. But since we have no modeling in the graph, there's no information about the other registers. There's actually a register that controls the loop, almost like a for loop. So at some point that register will hit 0 or something, and then we'll break out of the loop. But in the graph we don't know this. So it looks like if an interrupt arrives at 2801, now we will never get to the handler, right? So that's the reason why there are 5 nodes that I have drawn with this different kind of edge. So what this is signaling is, if you're just modeling the program counter and the IMR in this way, control from the point of view of the analysis may never get to the handler in sort of infinite latency, right? That's not exactly what we want. So that's one of the effects you get out of this. We made a choice. We're just modeling the program counter and the IMR, 18 bits, roughly speaking, and there are just cases where it's not going to show that the latency is finite. It's just going to give back infinite latency. Of course, for many other nodes, the latency is finite, and we can then, with a graph search, compute what it is. So I'll say a few words about how we built this graph. So actually, the idea, I've listed some of the major instructions here, which is sort of the critical ones that most of them are, you can see there's one called various at the top. So those are pretty much all the ones that don't touch the stack. Don't put something on the stack, don't take something off the stack. The other ones are the things that actually do something to the stack. And you will see that I have listed on the edges, the edges have labels, so I've listed that in the second column. And the idea is again that bang 1 means, and this thing puts 1 byte on the stack. Bang 2 means it puts 2 bytes on the stack. And I've written in brackets what is the kind of stuff it puts on the stack. So that's nice to know. And then the question mark is taking things off the stack. And so you can see that there are 4 different things in our view that puts things on the stack. So there's certainly call and interrupt calls. So the call is an explicit instruction. The interrupt call is something that happens automatically. But it all becomes edges in the graph in the end anyway. And then we're distinguishing between 2 kinds of pushes. And the reason is that in the way you program this processor, it's handy to sometimes take the IMR and push it on the stack. And then you pop it off again and sort of restore the IMR to the register. And since what we are doing is that we are in every node, we want to know the exact value of the PC and the exact value of the IMR. Pushing it on the stack means, great, so there goes the value of the register, but the register didn't change, so that's fine. However, now when we later on pop the thing back from the stack, if we don't know what it is, then suddenly you can imagine a node in the flow graph that at the point of where it should say bits for the IMR, it would say question mark, or we don't know what it is. And so we cannot live with that. We need to know what the IMR is all the time. So what we're doing here then is that we're saying, okay, we'll distinguish between the instructions that say push IMR and then the ones that says push something else. The one that push something else, we don't care about those. So that's why it says UNK, it means unknown, right? We don't care what they push. We just know that they push 1 byte. For the ones that push the IMR, what we'll do is that we will make a connection. So this is actually what happens here. We will make a connection so that the edge from N to M is an edge where we push an IMR to the stack. And then the edge E on the top there is one that says we're not changing the stack here. And then when we get to the pop IMR, so you imagine that in this node P in the graph, that's the node for an instruction that says pop IMR. What we're going to do now is that we're saying, but we know from the graph's point of view, we know what's on the stack because it's this IMR value over to the left there. That value is the one that's pushed on the stack. And what we'll do now is that when we now take this dotted edge or dashed edge going down to Q, what we will do is that we will say, great, in Q, we know what the IMR is the one we push from the stack. that was pushed on the stack before. So in that way, when we get to Q, we will again have, as we want, perfect knowledge about what the IMR is. It's just that it took an unusual round of being put on the stack, taken off. And then we will do another thing which is actually typical in normal interprocedural flow analysis of C programs, is we will have this edge at the bottom there that I've labeled E. So E still means doesn't touch the stack. And this E is what is usually called a summary edge. And what it does is that it summarizes what is going on between N and Q, from the point you put something on the stack to the point where you take something off the stack. And the summary is, well, in the grand scheme of things, nothing happened to the stack. In between, of course, the stack grew and then it went down again, but after all this has been done, nothing happened to the stack. And we can summarize that with this E edge. This is the same thing that goes on so we have similar diagrams, for example, for call and return. So there will be a call on the left side, then there will be an E that says, and nothing happens to the stack here, and then there will be a return. And then there'll be a summary edge saying, well, connects the call point and the return point. And so this turns out to be nifty for the kind of things we want to do. So I'm not going to say more about this, but this is a standard trick in interprocedural analysis. Anyway, so we have to make certain assumptions. So we are working on a processor where there's actually an indirect addressing mode for registers. So just like you have indirect addressing mode for RAM, when you're working on a sort of more conventional modern processor, on this processor, in some sense, the register and the RAM is sort of the same thing. And the designers chose to have an indirect addressing mode, so you can have a register that points to another register. And the thing is that there are 3 registers we need to be absolutely sure are not sort of manipulated behind our back, because then we lose control over what the graph should look like. And that's certainly the IMR register, so we don't want anybody to mess with this unless we know about it. The IRQ is the one where the interrupts wait until interrupts get turned on, so we don't want people to mess with that as well. And then of course the stack pointer. So the whole graph is based on that we know exactly when things are put on the stack and when they're taken off the stack. So we're making assumptions about that people don't go around and mess with them in indirect ways. And actually we make more assumptions. So for example, we don't want people to go and set bits in the IRQ register. It's a register like all other registers, so bits do not get set just because interrupts arrive. You can set bits. We don't want that to happen. And for the stack pointer, we don't want people to suddenly go and change the stack pointer. We want the stack only to change because of push and pop and call and return and so on and so forth. So unfortunately we cannot check these assumptions because we're not modeling the other registers, and if one register happened to point to the IMR and you make an indirect manipulation now via that other register, well, we don't know what's in that register because it's not in our graph. So we're sort of relying on that the programmer is disciplined and doesn't start to do those kind of things. We would like to check this, so this comes under future work. Now we don't. So I want to say a few words about how to actually do this interrupt latency analysis. So the point is that there's a handler. Actually, there could be more than one handler because let's see, there could be more than one handler in the graph. So in the program, there's certainly exactly one handler for each interrupt, but in the graph, the handler is sort of, in the program, the handler is designated by the program counter. So if you know what the program counter is, that's where the handler is. But in the graph, of course, every time there's a program counter, there's also an IMR value, and there's, however many bits are there. There could be, in the worst case, if there's 7 bits of IMR, there could be 2 to the 7 copies of the handler for a particular interrupt. So when I say handler for an interrupt, from now on, I'm talking about all the different nodes in the graph that have the start address as the program counter value in it. And in the particular graph you saw there was only one, so life is simple, but in for other graphs there could be more than one. So what I'm going to say is that I'm going to say, okay, we will just look now at the highest priority interrupt. So that's the one that has the biggest chance of being handled because it has higher priority than the other ones. And then I'm going to use H as saying in some sense we can think of H as the set of those nodes that are the nodes for the start address of the handler. So there could be more than one, sometimes there's only one, and however many there are, let's call them H, right? So now, what we're going to do is that we will paint or we'll color all of the nodes in the graph red, yellow, and green. So red means There is no way, if an interrupt arrives in this red node, there is no way that control will ever come back to a handler. So that's the last thing we want. So this is not even saying infinite interrupt in some sense. It's saying it's really infinite. It's just, you will never get there. Green, on the other hand, are the ones where no matter what happens from now on, if the interrupt arrives here, it may not be handled immediately, but it will for sure be handled in the future. And then yellow are the other ones, right? So the yellow ones are the one with the round, thick edge in the graph. Those are the ones we don't like. We don't. So in some sense, red sounds like a programming error. We don't want the program to be able to go off in a corner and suddenly just turn off interrupt and never turn them on again. That would be red. So we don't want that. That would be something we would first get rid of. And there were no red nodes in the graph you saw. The second worst thing is yellow nodes. And as you saw, even with the analysis we're doing now, when we're modeling 2 registers of the processor, we cannot always get rid of all yellow nodes. There will be some nodes that are green, some nodes that are yellow. But for those nodes that are green, we can then do a simple graph search and find out what is the longest path from this green node to a handler. And so that's something there. So I just want to say one more thing about this issue of what does it mean that you are in a node and and it should really be green. No matter what happens, computation will reach a handler. What does this really mean? So the observation is that if you have a node where interrupts are turned on, or let's say that we're now just looking at the highest priority interrupt. So let's say that this interrupt is really turned on. The master bit is turned on, and the bit for that interrupt is also turned on. If an interrupt arrives in that node or is waiting when you get to that node, this interrupt will be handled. Control will go to the handler at that point. So really what we're talking about is not just reaching the handler. What we're really talking about is reaching a node for which there is an edge to the handler. The edge is sort of there if and only if the interrupt is turned on. So what we're up to here is actually a little refinement of the specification, that we will say that nodes are ultra green. So the ultra green is also green. So it's ultra green if there's an edge directly to the handler, and those are really those are really the nodes that we're interested in hitting. If we are somewhere and we can get to a node, and we're sure that we will, no matter what we do, we will always get to a node that has an edge directly to a handler, even if it has other edges going in other directions. We know that the interrupt is going to be handled. So what we get is now a sort of a variation of the specification that says green means that you're already at the handler right here, or it's inevitable that you will get to one of these ultra green nodes, which are then sure to move on to the handler. And now one can wonder how expensive is it to color the nodes red, yellow, and green. Once we know that we're looking at a green node, it's easy enough to do a graph search to find out what is the longest path to an ultra green node. But to know whether it's yellow or green or red is a different matter. And this is where just a little bit of specification language comes in. So there's something called computation tree logic, which is a logic that exactly talks about graphs that we're looking on here, control flow graphs. And in that graph, in that logic, you can write down exactly what I have been saying about yet red and yellow and green and ultra green, and it comes out like this. It doesn't matter quite what these symbols mean, but they say exactly what I was saying before. And the key is that in that logic, it's known that no matter what you throw at it, if you have a graph G of some size and you have a formula written in this little logical language there, then you will be able to color the nodes always in polynomial time, actually in time that is the size of the graph time, in the worst case, in the size of the graph times the size of the formula. And as you can see, the formulas that I'm using here are very small, so that's not where you get a big complexity hit from. So this is saying no matter how bad the graph looks, no matter how complicated it is, we can color the graph red, yellow, and green in polynomial time. So that's what we get out of this. So we have, of course, an implementation of this that is sort of hand-coded. So let me give you a few measurements here. So these are, so as you see, there are 8 programs listed there. 7 of them are these programs we got from this company up in Milwaukee, and the last program was one we wrote to be a little bit adventurous. So it turns out that when we look closer at the 7 commercial microcontrollers there, they're written in a rather conservative style. And conservative means that they will have interrupts turned on, then they will get to the handler when an interrupt fires, and then it would be very conservative about when they turn on interrupts again. So one of the ways you can see that this is the case in the graph with the numbers here is, first you look at the number of nodes in the graph. Well, that's sort of the critical thing. The number of nodes, except for one program where it's 5,000, in many cases it's just 1,000, 1,500. And these programs are sort of 500 lines long, 1,000 lines long, something like that. And you see the number of times a line gets copied is exactly sort of the number of times that there are different IMR values that you can sort of get to that line in different circumstances, where the circumstance is what is the IMR at this point. And you can see the number of nodes is not much higher than the number of lines, so the IMR doesn't change that much, which is another way of saying it's the program is not very adventurous in the way it turns on and off interrupts. So these are rather conservative programs, and the example program at the bottom was written to be more adventurous. And adventurous is in a positive sense, because what we want at the end of the day when we have these interrupt-driven systems is we want them to be responsive. We want them to have low latencies. Of course, here I'm only going to show you numbers later on for the highest priority interrupts, but there are various interrupts at lower priorities also, and we want all of them to have good latencies. And the more they're turned off all the time because you're worried about that the stack grows too high or something like that, the longer latencies you will get, right? So these are conservative programs, and what you'll see that the number of edges is typically on the order of 2-3 times the number of nodes. So what this means is, again, when you look at the graph, typically if there are 2 edges, it means that there's an edge going to the next regular thing in the program, and then there's an edge going to an interrupt handler. So that's sort of the usual 2 kind of edges. And of course there could be more than two regular edges if it's a kind of a branch statement. We're not modeling whether you're branching this way or that, so we just have 2 edges going in both directions. So you get sort of 2 or 3 edges in this way. What you see in the time and the space columns there is that to just build the graph, it takes 4 or 5 seconds, and actually to run all the rest of what we're doing, it's sort of hand-coded to be fast, and it's not going to take much more time. And the space, it's running in Java, so it's running on top of a virtual machine. So actually most of these 30-40 megabytes that it uses is for the virtual machine. The amount of space we're using for the graph, I mean, how much space can it take to represent 2, 3, 4, 5,000 nodes and same number of edges? It's not going to take much, 1 or 2 megabytes at the most, even if you use quite a bit of space for those. So actually most of the space is taken up by the virtual machine. Now let's look at the stack size analysis here. So the upper column is the column we get by taking the programs, building the graph, and then doing the same kind of thing I did for the graph of looking for the path in the graph that has the longest sort of sequences of pushes. And when you get down to the row of fan, you will see that it says NA. So NA here means there was a cycle. There was a cycle where you keep pushing along in the cycle. So this one is saying unbounded stack. So our analysis was not good enough to detect that probably, at least the designers, as far as we know, think that the stack is always finite. These things have been running in many thousands of installations around the country for years, and they have never crashed in funny ways. So in practice, probably the stack is finite. But our analysis cannot detect it in this case. In the other cases, you see these stack sizes of, for the 6 commercial programs we're down to now, the maximum stack size is 18, which is of course not very much. You know that each interrupt puts 3 bytes on the stack, so clearly interrupts are turned off enough that these interrupts are not interrupting each other a whole lot. The last example program was the more adventurous one, and you can see the stack. This program is much shorter than the other ones. It's about 60 lines of assembly, where the other ones are much longer, but still the stack size goes all the way up to 37. Then we have the lower column. So we wanted to find out how good is the analysis. So what we did was that we wrote a complete software simulator for the Z86 that simulates everything in Java. and we also wrote some simulation for the external devices that the microcontrollers are controlling. And then we started running the simulator on the program, and we sort of fired interrupts. We have sort of a device for in a software way, firing interrupts at the microcontroller and see how high we can push the stack. So we actually have a little genetic algorithm system that finds really bad interrupt schedules that try to push the stack as high as possible. And as you can see, the lower bounds are pretty close to the upper bounds. There are a few cases where they don't, well, sometimes they don't match, sometimes they match. Or at least I see one case where they match, or two. And so that's great. And in the other cases, well, so there are reasons why they don't exactly match. But you can look at it from the point of view of the designer. So you've just written the program, you run it through the tool, you run it through both tools. You get one tool for the upper bound, the other tool for the lower bound, and you get these numbers. So these numbers will tell you about how much stack space you should set aside for the stack. That's the upper bound column. That's a guarantee you will never need more. And the lower bound column says, yes, you will really need most or all of the space that the upper bound says, right? So it's really useful in the sense that you will get information about how much you need and what an upper bound is, and that you will actually need it. Now, for the kind of type stuff, what this is all about is, if you go back a little bit here to my big picture, what we're doing here for the type checking of things on the stack, what we're doing is that we're saying, well, if we have a situation like this, it could be that the node for P there was actually for a return instruction. So this would be a disaster because it would mean, hey, we're trying to do a return where on top of the stack there's an IMR value. So what we're doing is that we're saying if we ever run into a situation in the graph where that could happen, where the push and the pop don't match up, we will call it a type error, and the tool will report an error. And when we go back and look at these programs here, actually there was never an error. And if you look at the little graph that I showed you for the little program, that's actually never an error. It's always the case that if you push something and then wander around doing nothing to the stack and then do something that takes things off the stack, the push and the pop will match up. Call will match up with return, push IMR will match up with return IMR, and so on. The last graph here, the last table here talks about the colors and what latency we get out. So the latency is in machine cycles, and on this processor, one machine cycle is 1 microsecond. So you see we get latencies that are all less than 1 millisecond, so it doesn't sound so bad. And you see that 0% red nodes means there are no red nodes. So no matter, for all of these programs, it's always the case that you will have a path to a handler. However, it could be that on that path there's a loop that is infinite, and so it looks like you will never get there, even if the loop in practice is always finite. So those are the yellow nodes. And I have something here called ultra yellow. So ultra yellow are the yellow ones that are on a completely yellow cycle, and then there'll be other yellow nodes that are sort of leading up to that cycle. So all the ultra yellow nodes are also yellow, but the ultra yellow nodes are interesting because we want to get rid of yellow nodes. So the first ones we will attack are the ultra yellow nodes. So if we can get rid of a whole ultra yellow cycle, it will mean that all the yellow nodes that lead up to that cycle, they will go away as well. So future work is to turn yellow nodes into green nodes. And you can see the green nodes, it ranges all the way from 19% up to 79%. So sort of for smaller or larger parts of the graph, depending on which program we're looking at, we will be able to say for those parts of the graph a finite bound on the latency. And for other parts of the graph that are yellow, we won't be able to say. But we're working on turning more yellow things into green, and hopefully one day I can give a second talk where there won't be a yellow column, or rather the yellow column will be all zero. So what we need to do is model more of the machine. So modeling the PC and the IMR has been great. We have it leads to great upper bounds on the stack sizes. We get all the type checking done that we want to, no type errors there. But for the latency analysis, we get these yellow nodes. So we need to do more. So we need to, for example, for a loop that is controlled by a register, what we need to do is model the loop variables. So we need to have loop variables in the states, in the nodes. And other things we would like to do is we want to have more explicit types in the program. So there are reasons for that, which I won't go into here. And eventually we would like to scale this up to bigger processors. So right now we are modeling IMRs that are 7 bits long. If we instead move on to the Motorola 68000 family, we will need more bits. So actually there are some versions that process all the way up to 23 bits in the IMR. And of course the programs are much bigger, so we will get many more nodes just because the program counter can have many more values. Any questions? So I got no interrupts during the talk, which was, well, but now's your chance. Okay. Well, thank you for coming.